Everyone can see my screen, right? Is my screen like visible for you all?
It's not sharing.
It's not sharing?
Yeah.
Wait, let me just share it again then. Is it now presenting? I'm like from my side it says that. Can you all see my screen now?
No, man.
You still can't see the PDF I'm opening?
No, there is nothing on your screen. It's just you.
It's just... Tajdeep, can you please confirm that are you like seeing anything on the screen? Because from my end, I am representing it.
Yeah, it's visible.
Okay, Sabit, is it like clear for you now? Like, can you see my screen now?
No, I'm just seeing. Wait, let me send a screenshot.
Okay, sure. Are you in your phone or PC or laptop?
I'm in a phone.
You're in a phone. I don't know.
Yeah.
There's nothing much about like glitching in this, I guess. Wait, let me just look up to your screen. No, it really doesn't show anything on your screen.
Yeah, now I can see.
Can you see it, right? Okay. Maybe it was just some internet issue. So, okay, I'll start. So this is the lecture PDF, like everything written mainly. Everyone can if you can just turn off your mic if it doesn't have any questions, and just turn it on when you have any questions, right? So this is basically the PDF note that will be uploaded in our Google Classroom. Like after today's class is basically a trial class, so that everyone can understand that if they are going to actually be capable of adjusting with my explanation or not, right? So these are the entire PDF notes that I will be providing for my students. So there will be one PDF notes for you to go through all the topics that are might related, or like they have the mark scheme words or the simple definitions that might come into your questions main question paper, and few examples that I will be solving inside the class, and I might give you some classworks inside from this PDF. Like there are one example, like 4 to 3 examples in each PDF, and I would be like solving the first 3, and the last one will be given to you all as a classwork, and then you will have to just solve it and click a picture of it and post it in our messenger group, right? So, and I will try to explain every part of it using the OneNote. So here I will try to explain everything like right on the screen and explain every point of it, and the written OneNote PDF will also be uploaded in our classroom again. And all the classes are going to be recorded. All the recordings are going to be uploaded inside our classroom. So you will basically get every bit of the resources that I'm going to use to conduct the classes and to provide the lectures and worksheets. I will be providing like simple worksheets, like small worksheets on each topic, and for the worksheets I will provide solution classes, right? So I'm hoping that by the end of February now. So by the end of April, we will be done with our Unit 4, and then we can start with our Unit 5 from May, June, July. And by the end of July, we will be done with our Unit 5 also. And from August and September, we have our question paper solving session. And Unit 6 won't take much, it won't take a month to complete Unit 6. I would take maybe maximum time would be 1 week or 2 weeks to complete the entire Unit 6 session. And after that, we will be conducting our mocks and question paper solving classes. I will be solving question papers from 2016 to the latest year, and for each unit I will totally solve, give you a walkthrough for the first paper. That would be basically the January 2016 Unit 4, Unit 5 and Unit 6. And after that, after solving the January 2016 paper, from June 2016 to the latest year, I will give you those years as exam homework, and you have to submit the problems. You have problem in 4, 5, 6 for a certain year, and I will be discussing those problems inside the class to clear out the problems you faced while solving that question. and we will be conducting 5 mocks for each unit. For example, 5 mocks for unit 4, 5 for unit 5, and 5 mocks for unit 6. So in total there will be 15 mocks for the A2 session. Is there anything else that you guys want to know about the classes, how it will be conducted and everything?
I'm good.
Okay, then
Ma'am, is this the final timing you're giving?
yeah, the classes will be at the night and around 10 p.m. Right.
Okay.
Yes, sorry.
Okay, I said okay.
Okay. Actually, I have universities and other works in the morning, so I actually tend to take all the online classes during the night.
Okay.
Okay. So let me just go back to this worksheet. Like, we are already familiar what momentum is, right? Like the basic definition, it is a product of mass and velocity. Like if I just draw two objects to first explain what momentum is. For example, we can explain momentum in terms of one object, we can explain momentum in terms of two objects, and then again we can explain momentum in linear motion, and we can explain momentum in angular motion. The angular motion is basically the 2 dimensions of momentum, right? So the diversities of momentum are first we can explain it using one objects. There could be one object or two objects, and again momentum can be explained into the direction of motion. If it is only involved with one direction, then we refer to that as linear momentum. And if it is referred to with angles and everything, then we refer to that as two-dimensional. Right, angle. So the basic concept that we are going to start momentum with is with using one object only. So for example, if we have an object at this point, let me refer this point as point A, and we are actually just involving with this specific object. So for example, if this point this object was at point A when time was 0, and this object just rolled down to a further different position at this point, and this point is referred to as point B, and the time for this point can be like around 4 seconds. So we can understand that object rolled from point A to point B in 4 seconds, and the velocity for object at point A might be like 10 meters per second, and the velocity for object at point B might be 25 meters per second. And obviously the mass of the object didn't change during the entire journey, so the mass was throughout the entire journey could be same, like 2 kg. So when we see these kind of diagrams, we always refer to the point that it is somehow related to acceleration, maybe, right? Initial velocity minus final velocity divided by time. But here we are acceleration obviously deals about the entire journey. You're taking information from the start of the journey, initial velocity, and you're taking information from the end of the journey, for the end of the journey, that is the final velocity. But if you are asked to give you informations about how the entire position or the movement of the ball changes over each second, then you cannot just explain it using acceleration or using force, right? Then what you have to do is stick to the concepts for momentum. For example, if you want to know that how the object rolls down in 1 second, for 1 second there will be no change in acceleration. for 1 second there will be no change in force. So for just specific at exactly point A, to get the values for the motions of it, you can use the ideas for momentum. For example, the momentum for object at point A will give you the entire directions of how the object was moving, in which direction the object was moving. These are the things that you will get from just point A, for just point A, not for the entire journey. If you are focusing on the entire journey, like if you are taking entire informations from point A to point B, then you are actually working with the entire journey. You are working with every concepts inside the journey, right? Then you are going to use force and acceleration. But if you are asked to give informations about in which direction the ball was rolling at specifically point A, then you have to use the concepts for momentum, so that will just stick to one certain point, not the entire journey. So if we are to ask the value for the momentum at point A, we are going to use the basic equation mass into velocity, right? So momentum is always referred to as P equals to mv. Here mass would be 2 kg and the velocity would be 10. So the momentum for the particle at A would be 20 kg meter per second. And again, if you are asked to find the momentum for point B, excuse me, just give me one moment. Okay, sorry. So as I was saying that if we are working with momentum for the particle in position B, then it will be P equals to mv, and the mass would be 2 and the velocity would be 25. So if you multiply it, you get the value for 50 kg meter per second. So these are the informations that you get for every specific point. Remember that momentum is a vector quantity, and vector quantities always depend on two criteria, that is magnitude and direction. Right, let me just write it down over here. Vector quantities depend on first magnitude, and direction. So when we were actually starting to calculate the value for momentum for the particle at every point, at point A or at point B, regardless at whatever direction the particle was moving, we obviously going to consider one direction to be positive. For example, for both points A and B, I considered direction towards right as positive. So I'm taking direction towards right as positive. And as we can see that the momentum for particle at A is plus 20 and the momentum at particle at B is again plus 50. So it refers to, from our calculation, even if we do not have the informations from the diagram or anything, from our calculations we can see that the particle was giving a positive value for momentum. That means the particle was obviously rolling down towards right for both at point A and B. But for example, if this value would have come in negative, like negative 50, what would it mean? That it means that at particle B, the direction of the motion of the particle might have reversed. That's why it's giving a negative sign. Is it clear, like how can we use momentum to give informations for a specific point in a journey? Is there any question regarding this up to this point?
No, ma'am.
Okay, I mean, these are basic concepts that we already have, right, from our previous classes we have studied till now. So this was the introduction for momentum. But for momentum of a particle, obviously we can see that momentum changes over time. We are obviously sticking to one particle that is rolling down from point A to point B, but the momentum is not same. Right, for point A there is a different momentum and point B there is another different momentum. So if we are to calculate the change in momentum, like how the momentum changes over time for a specific particle, we can also calculate that. Change in momentum is basically final momentum minus initial momentum. Now, like if you have, like we have already the values for final momentum, we are taking the point A as initial position and point B as final position. So if we are like to calculate the change in momentum for this specific particle, we have to subtract PA from PB, and we will get 50 minus 20, that would be 30 kg per meter second. So now change in momentum doesn't have any different unit or other things. It just have a different equation, right? Normal momentum has an equation for mass into velocity, and change in momentum has an equation for initial momentum subtracted from final momentum. And the units are going to be same for every for both the maths, both the formula, and the concept is again going to be same. Like it is giving a plus direction, plus value. That means that the change in momentum indicates that finally the object was moving towards the right, and if the change in momentum would come into negative sign, that would mean that if, eventually the particle would have rolled to the left. That's why it would give you a value for the negative magnitude of momentum. Now change in momentum is again related to force. We have already seen the derivations, but I'm still gonna like give you another walkthrough for it. How force is related to momentum. Force and momentum. So for example, if you are working with momentum of this particle from position A to B, and now you have calculated momentum for each point, and now you have calculated momentum over the entire journey, like change in momentum over the entire journey. Now you want to calculate like how the momentum changes with time, right? So when you are like calculating the value for how momentum changes with time, you would actually get the value for rate of change of momentum. Whenever you are trying to calculate the change in momentum with time, you would get the value for rate of change in momentum. So you can like write it down as change in momentum is delta P over time, rate of change in momentum by time. Now the equation would be mv minus mu. The final momentum is referred to as mv with the final velocity, and the initial momentum is referred to as mu with the initial velocity, and obviously divided by time. Now using the simple factorization formula, change in delta P over T, you can take m common from the numerator, and it will look like mv minus u over T, and delta P over T would look like m into v minus u over t, which is basically the equation for acceleration. So you can obviously write delta P over T is equals to ma, and mass acceleration was the equation for force. So you end up with rate of change in momentum is equal to force. So this is basically the relationship between force and change in momentum. So the rate of change in momentum is always equal to the force of the overall object for the entire journey. Is this relation clear? Is there any question?
No, ma'am, it's okay.
Okay, so up to this point it's totally clear. So if we move to our entire sheet here, like we can see that the entire derivation is again given, like how force and change in rate of change in momentum is related, how Newton's second law and momentum is related. I have given the entire walkthrough in that like OneNote file. So this was it for the time being. I'm gonna solve example 1 for this. It says a ball of mass 0.25 kg hits the floor with a velocity of 2 and rebounds with a velocity of 1. The ball is in contact with the ground for 0.1 second. So part A wants you to calculate the value of force that the ground exerts on the ball. So if I draw the diagram for the entire scenario, example 1, Like this is the entire scenario of a bouncing ball. It was thrown from a point certain height above the ground, and then it hits the ground and again rebounds at a different speed. So if I just move to this point, it says that the mass of the ball was 0.25 kg. It hits the ground with a velocity of 2 and rebounds with a velocity of 1. So if I just move here, it was hitting, like it was falling to the ground at a velocity of 2 meters per second, and it rebounds from the ground at a velocity of 1 meters per second, right? So this was the velocity, like with which it hits the ground and with which it rebounds from the ground. And why does it rebound from the ground? Because obviously there was an force exerted on the ball by the ground, right? So why the ball rebounds? Is because there is a force exerted on the ball by the ground. I wrote it down over here because I will need this explanation again for the next part of the question. So the entire thing was exerted on the ball by the ground, right? So the force was exerted on the ball. The ball experiences that force from the ground. So if you are to calculate the value for change in momentum, or sorry, what the question asked you about, calculate the force that the ground exerts on the ball, right? You have to calculate the force exerts that the ground was exerting on the ball. So if you can use actually concepts for moment impulse here, and I haven't explained impulse up to this point. I should like do this example a few minutes later. I'll first explain what impulse is, and then we will actually move to this example 1, right? This example 1 consists of the concept for impulse, and I haven't actually explained impulse yet. Impulse is in this second portion, as you can see. So I'll first explain impulse and then move back to example 1. So before impulse, we have these laws of conservation of momentum. Law of conservation of momentum always states that the particle, like if there is no external force acting on the particle, the momentum before collision, after collision, always have to be equal to each other, right? For example, for this one, there is no collision, right? For this scenario, I have stated one particle is just simply moving from point A to point B. There is no two particles colliding with each other. There is no change in motion. When there is change in motion for the particle B, for the particle at different points, because their speed are not same, right? Its speed changes over the journey, but still the particle is not colliding with any other object or particle, and there is no change in direction. So we cannot use the concepts for conservation of momentum for this one, as there will be no collisions involved. But for example, if we are let me just give some space for example 1 and move to the concepts for laws of conservation of momentum. So laws of conservation of momentum. Here you can see like there will be different type of scenarios. The first scenario here will be like the most simple scenario that we can use to explain the conservation of momentum. Like this is mass 1, this is mass 2. We are now dealing with two different masses, mass 1 and mass 2. And for example, if we are considering mass 1 to be stationary, so the velocity for mass 1, so mass 2 would be 0. And if you are considering mass 1 was moving with a 10 meter per second towards right, this is how the entire scenario before collision would look like. And now if you are moving, like dealing with after collision, So if the mass for M1 is around 1 kg, and if the mass for M2 is again 1 kg, so the mass would be same for before and after collision, right? There will be no change in mass before and after collision. So if you are working with like momentum before collision, after collision, according to the laws of conservation of momentum, the values should be same for both before and after collision. For both before and after collision. Amistat. Sorry for that. So we were working with before collision. Momentum before collision. So it will be like M1 U1 plus M2 U2. So it will be 10 into 1 plus 1 into 0. So the momentum before collision is basically 10 kg per meter second. Obviously we can understand that, but after the collision we have to calculate that also. So it will be again M1 V1 plus M2 V2. I'm not taking much consideration about directions because everything is moving towards right? So obviously we are taking direction towards right as positive. So the final momentum for after collision would be again 10 kg per meter per second. So we can clearly see that momentum before collision and after collision is exactly same. There is no change in value, and this is because that no external force was acted on the two objects while the objects were colliding to each other. Like the entire scenario was that object 2 was stationary and object 2 was moving, and then as object 1 was moving, object 1 hit object 2, and after hitting they started moving towards right separately with the same speed. They started moving towards right separately with the same speed. And with this example we can clearly see that how for our laws of conservation of momentum, when no external force is acting on the collision, on the particles during collision, the conservation for momentum is going to happen. Like momentum will obviously be conserved. There will be no change in momentum before and after collision. Is this example clear?
Yes, ma'am.
Okay, if this scenario 1 is clear, I'm going to use another scenario. Like for scenario 2, there will be again before collision, after collision. Now, unlike the previous example, here the two particles are moving but in opposite directions before collision, and after the collision after the collision they are moving in the opposite direction. For example, here the mass is still again going to be like 1 kg for all the particles. And now if we are to calculate the concepts for before collision, after collision, we have to now take specifically right, that we are taking direction towards right or direction towards left as positive, because here both the directions are involved, right? So I am taking things for taking direction towards right as positive. So if we are moving with before collisions, we have to deal with like what? If you are taking direction towards right as positive, that means before collision m1 will be positive, m2 will be negative because it was moving towards left, right? So we can write m1 u1 plus m2 minus u2. So the final equation would look like m1 u1 minus m2 u2, and it will be like 10 minus 10, and the final value for the before collision momentum would be 0 kg meter per second, and for the after collision it will be m1 v1 plus m2 v2. Now here v1 will be negative because now particle 1 is moving in the negative direction towards left. So the final would be minus m1 v1 plus m2 v2, and if you put in the values it will be negative 10 plus 10. Obviously the final momentum is again going to be 0 kg meters per second. And this is again another example referring to us that momentum before collision and after collision is same as long as no external force is acting on the objects during collision, right? This is another example, and the last example that I'm going to show is that like after collision the particles join together and start moving in the same directions together. So scenario 3, m1 m2, the value for the initial one, let's assume that 10, they are both traveling at the same direction, and after collision the both particles combine, like join together and start moving at a certain value for like v, as they are both combined together and started moving in the same direction, so they will have the value for velocity same, right? So the value for velocity would be like 50, not 50, so 25. .5 meter per second, and the masses are still same, 1 kg, 1 kg, and 1 kg and 1 kg. This was m1, this was m2. Now before collision, after collision, before collision it will be m1 u1 plus m2 u2. Now again here direction really doesn't play a role because everything is moving towards right. So the before collision entire equation would look like this, but after collision it will look like m1 plus m2, and the entire thing would be multiplied with just one single velocity because after collision both the particles combine together, so their masses will be added together and there is one velocity for both, right? You can obviously write it separately like this, like our previous one, m1 v1 plus m2 v2, because the velocity is going to be same, right? m1 and v1 is going to be same for both mass 1 and mass 2. So you can obviously take v1 common, and that would be like m1 plus m2. That would be just a summation of their masses. So for the last scenario, when the particles combine together and start moving in the same direction with the same velocity, the collision, like before collision, concepts and equations are still same, but after collision it will change. There will be just one single velocity and multiplied with the addition of the two masses. Is this scenario 3 clear?
Yes, ma'am.
Okay, so this was it, like different collisions we are working with, and now we will be like moving to impulse. Impulse basically like focuses on the forces that are involved during the collision. Like during the collision, what are the changes that happen to the two particles and how the forces are applied on each particle. So during collision, for example, if two particles are, doesn't matter if one was stationary and the other was moving, and if they were moving in the opposite direction, it really doesn't matter what their before collision state was. But during collision, for example, if this was a particle and this was another particle colliding with other particles, obviously. So if it is mass 1 and it is mass 2, so during collision, mass 1 will exert a force on mass 2 and mass 2 will exert a force on mass 1, right? So I know my words are very confusing, so let me just write it down at the corner. F1 would be force exerted by mass 1 on mass 2. So force exerted on mass 2. So I am referring to that force as blue line. So this is the force exerted by mass 1 on mass 2. This is F1. And there will be another force towards the left. And this is the force exerted by mass 2 on mass 1. So this is going to be F2. By mass 2 on mass 1. So these are the two forces that act on the particles during collision. Whenever two particles are colliding with each other, one particle will exert a force on the other particle, and obviously according to Newton's third law, the first particle will eventually receive a force of equal magnitude but in the opposite direction. So F1 and F2 are equal to each other, right? So F1 and F2 are equal to each other according to Newton's third law, right? Newton's third law. N3 law. Okay, so if we are dealing with momentum, obviously the particles collide for a certain amount of time. They will be stick together for a certain amount of time, and after that they might pull apart from each other, or they might start to moving in the same direction like in scenario 3, but they will exert F1 and F2 on each other for a certain period of time. So the forces are exerted on each particle for a specific amount of time. So they have a time involved in it. For example, if you are to calculate the impulse for each particle, the impulse is in order of respect for each particle. You have to calculate impulse for M1 or you have to calculate impulse for M2. So if you are to calculate impulse for M1, you can calculate using it impulse M1. The formula is force into time. So it would be for M1, the force it feels, that is the force we are going to working with. For M1 we are not going to take the value for F1. For M1 we are going to working with F2, because this is the amount of force that was exerted on M1, right? So for impulse in M1 we are working with F2 and time, and for impulse in M2 we are working with F1 and time. And again we are gonna take direction towards right or left as positive. So if you take direction towards right as positive, that would make F1 positive. So impulse for impulse for mass 2 would be positive, but impulse for mass 1 would be negative, because the force exerted on mass 1 was in the opposite direction, like it was in the right, and it was in the left, and we considered right to be the positive. So it will have a negative impulse. It really doesn't mean that the impulse become negative. It just means that mass 1 feels a force or impulse in the left, and mass 2 feels or experiences a force on the right, right? So these are what these signs represent. If F1 is positive, it indicates that on mass 2 the force was exerted towards right, and if F2 is negative, it represents on M1 the force was exerted in the left direction. Is this clear up to this point?
Yes, ma'am.
Okay, so the unit will obviously be Newton's second, as we are just dealing with force and time. So it will be Newton's second. And again we can calculate impulse with change in velocity too. For example, if we are working with impulse for mass 1, like the initial velocity for mass 1 was like 10, and the final velocity, so like let's not give any values for this point. Like the initial velocity for mass 1 was u1, and the final velocity for mass 1 was v1, and again the different velocities for mass 2 will be labeled as u2 and v2. So v2. Right, let us assume that before collision, mass 2 was moving in this direction, mass 1 was moving in this direction, and after collision they start moving in the direction of the force. Like F1 was towards right, so the velocity for mass 2 was right, and the force was in the direction of left for mass 1, so the velocity will also be in the left. So we can also calculate the impulse for each particle using the change in momentum concept too. So impulse for m1 is again can be calculated as m1 v1 minus m1 u1, right? You always have to subtract the initial momentum from the final momentum. This is what the equation for change in momentum was, right? If you just scroll up a little bit, you can see that the equation for change in momentum was final momentum minus initial momentum. So change in momentum can also be considered as impulse at times. So if you just move back, and the equation for impulse for mass 2 would be m2 v2 minus v1 v2, wait, it will be m2 v2, and the other one would be u2. So this is the impulse for mass 1 and impulse for mass 2. So you can calculate impulse using change in momentum or force into time. So the two equations for impulse are force into time or impulse can be calculated using the equation change in momentum, right? And the unit for this one would be Newton second, and the unit for this one would be kg meters per second. Now if we just move to our example 1 now, as the concepts for impulse, change in momentum, and like what conservation of law of momentum is clear, so we can now just move to our this question, example 1. Example 1 actually wanted to calculate the force exerted on the ball. Obviously working with impulse, right? It wants you to calculate the force that was exerted on the ball during the collision. We can obviously see, like if we draw a label diagram for this, during collision the ball exerts a downward force on the ground, and the ground exerts an upward force on the ball, right? So there will be a downward force on the ground. This is like from ball on ground, and there will be an upward force from ground on ball. So we have to calculate the upward force from ground on ball. So we can calculate it now using the equations of impulse. It was also given that the ball was in contact with the ground for 0.1 second maybe. Yes, it was in contact with the ground for 0.1 second. So in order to calculate the value for force for any direction, for example, if you are just going to involve with the concepts for ball only, so we can calculate the impulse for ball using the velocity first. The mass for ball was 0.25 kg. So it will be impulse according to mass and like change in momentum mainly. So it will be 0.25, and as there is like two directions involved, upward and direction, so upward and downward. So we are going to take upward direction as positive. So taking upward direction as positive. So what will you what will you get? Let me just first write the equation here. It will be mv minus mu, right? The normal equation. Now m was 0.25, v was -2, like the downward directions are represented as negative, and then subtracted with 0.25 multiplied with 1. So if you calculate it, you get a value of 0.25 into 2 is basically minus half, and the other one would be minus 0.25. Minus half minus 0.25, you get a value for negative 0.75 Newton, or like kg meter per second, whatever unit you want to use, meter per second. Now you have to use this equation for the next part of force into distance, force into time, to calculate the value for the force exerted on the ground, on the ball by the ground. So using that impulse, we have already calculated impulse to be 0.75. Now impulse can be written again in terms of force and time. Time was 0.1, so the force would be 0.75 over 0.1. So if you calculate it, 0.75 over 0.1, it will be 7.5 seconds, right? So here the 7.5 newtons, not seconds, newton. So this is the value of force exerted on the on the ball by the ground. Now again, if you just take the negative signs in consideration, you have negative here, and negative here. Why the value for impulse is negative here? Because when you calculate with reference to force, you are only involving with the force exerted by the ball, right? Now the ball exerted a force on the ground in the downward direction, so obviously it will give you a negative value. But as we were working with the force exerted from the ground on the ball, and as it was like in the upward direction, as we can see from the diagram beside, so the final force exerted from the ground on the ball was in the upward direction, so the value will be just 7.5 Newton. Is it clear? The force will be 7.5 Newton. What we calculated here, negative 7.5, was basically the force exerted from the ball on the ground, right? Force exerted from the ball on ground, and it was negative. So obviously from our calculation, the value for force will come to be a negative value. But as we were just involving in the upward force, that was the force exerted from the ground on the ball, it will be positive. Our final answer will be just 7.5 Newton. Is this clear up to this point?
Yes, ma'am.
Okay, so if this is clear, we're just done with part A. In part B, let me just move there. Part B says, state and explain the force that the ball exerts on the ground. So obviously we have already seen, right, according to Newton's third law, the force exerted by the ball on the ground will be 7.5 Newton in the downward direction. So for the second part, for part B, we have to explain our answer and also write the numerical value of the force exerted on the ground by the ball, that is the downward force, right? So it will be, according to Newton's third law, the force exerted on the ground by the ball was 7.5 Newton in the downward direction. Right. If there is any question for example 1 in part A or B, you can ask now. Is there any question for example 1?
No, ma'am.
Okay, so if there is no question, we have discussed about momentum, relationship between momentum and force, laws of conservation of momentum, the different scenarios involved in momentum, and our impulse concept. So let me just move to the file again. This is a force time graph, but before that we will try to solve example 2. Can you both try to solve example 2 and give me a solution for the example 2 in our messenger? Right, please try to solve example 2, and if you can't solve it, then I'll show the entire thing.
Okay. Right now?
Yeah, right now. You have to solve it and click a picture of it and send it to me in my messenger. As I've said before the class, I will be giving classworks inside the class, right? So I'll give you like simple examples that you need to solve inside the class and give me the like picture of your work solution inside messenger.
Can I not do it right now, please?
Why? You don't have any resources with you now?
Yeah.
Okay, yeah, I understand like this was an extra class, so okay, so I'll just try solving the explanations. Just wait a bit.
Okay.
Okay, so I'll move to example 2. A skateboarder of mass 75 kg running with a velocity of 1.5 meters per second jumps onto a stationary skateboard of mass 5 kg. Calculate the velocity with which the skateboard and the skateboarder moves off. Like we can see, obviously understand that the entire example 2 is referring to the scenario 3 of our laws of conservation of momentum. Right, if you just forgot, let me just scroll up. This was scenario 3, like for scenario 3, after collision, the particles combine together and start moving in the same direction. Right, so if we move to the question again, before collision, like the skateboarder is referred to as moving object or particle 1. This is particle 1, right, P1. So P1 has a mass of 75 and a velocity of 1.5, and skateboard was considered to be P2 or particle 2. It was stationary, so the velocity was 0, and the final mass of skateboard was 5. And after collision, obviously, as the skateboarder will be on top of skateboard, so the masses are combined together. 75 plus 5 would be 80, and they will move towards the same direction with the same velocity. So if you are supposed to draw a diagram for this one, example 2, so before collision and after collision, I'll always prefer that draw a simple rough diagram for these concepts. It just makes sure that you are not losing mark for the silly questions like this. So this was like skateboard which has a mass of 75 kg and a velocity of 1.5. And it had a mass of 5 kg with velocity of 0 meters per second. After velocity, the particles combine together, that is like 75 kg and 5 kg combined together, started moving towards the same direction with a velocity of v. Now I don't know the value for v, we have to calculate the value for v. Again, we still don't know that if that particles combine together and start moving towards right or left, right? I am assuming that after collision, the particles combine together and start moving towards right. Now, obviously, as I'm assuming that, I've obviously need to make sure that the final calculation also gives this information. Like this was moving towards right, so I am taking direction towards right as positive. Right as positive. So before collision and after collision, we all know that they have to be same, so we can just write it down like this. Before collision is equal to after collision. So before collision, the mass will be like 75 into 1.5 plus, it will be 0 because the velocity for particle 2 before collision was 0, and then after collision the masses join together into v. So if you multiply 75 into 1.5, that becomes 112.5 equals to 80v, and if you take v the subject, it will be obviously 112.5 over 80. So final velocity will be 1.41 meters per second. As we can see, the value is in positive, so obviously the assumption was correct. After collision, the two particles combined together and started moving towards the right. So our final value or final explanation should be written as the final velocity is 1.41 meters per second towards right. Is this clear up to this point? Is question number 2 or example 2 is clear to everyone? Is there any problem for example 2?
No, mate.
Okay, so we studied a lot of topics here. If I move back to this one, we still have force time graph to explain. Scenario
Me.
for firing. Yes, I think it's Tajdeed talking, right? Bolo?
Like one of the candidate is not here.
I'm sorry, I can't actually see the video. Yeah, maybe
Samir.
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 Yeah, maybe he left. That's totally fine. As I was saying that I have completed up to laws of conservation of momentum and impulse. Now we still have force time graph, and like force time graph is a bit tricky topic and we have to explain each point for the graph. Now scenario for firing a gun is very simple, just focusing on the laws of conservation of momentum. And after that we have elastic inelastic collision and link between energy and momentum. And then a graph, there are 4 explanations for the graph, and a final example for how a collision can be inelastic or elastic regardless that the momentum is still conserved, right? So I still need another class to like explain entire linear concept for momentum. So I'll just explain up to impulse in today's class, and from our next class we will start with force time graph and the other concepts. So if my explanation is clear enough for you all to understand, and if you want to continue, then you have to inbox me in my messenger or WhatsApp to whatever way you are connected to me through, and then I will just add you to the Google Classroom and start our class from Feb 1. Okay? Tajdeed, are you there?
Yes.
Okay, so I am actually gonna end today's class and give the recordings of this today's class